cosmic consciousness, extraterrestrials and UFOs, sacred geometry, ancient civilizations, spiritual connection, the quantum universe. All of these topics and so much more with your host, Sev Tuck, on Alien Spirit with Sev.
Hello, I'm Sev, and welcome to the very first episode of Alien Spirit with Sev. I am an author, a ufologist, an experiencer, a spiritual counselor, and an experiencer advocate. I created Alien Spirit to ignite our imaginations and to broaden our perspectives about the mysteries of life, and to help answer the questions, who are we and what are we doing here? The show broadcasts on the first and third Mondays of every month from 5 to 6 p.m. Eastern on KGRA and on my YouTube channel, Alien Spirit with Sev. I also have 4 special little mini shows. That's what I call them, mini shows. They're only 15 minutes long, and they're only on the KGRA network. The content of these mini shows cannot be seen anywhere else, only for the members of KGRA. I discovered my very first guest, Jason Padgett, 15 years ago. And in 2015, I saw him speak in Baltimore at the American Visionary Art Museum. And at the end of his talk, he was taking questions. So I waited, and there were a lot of questions. So we didn't get to mine. And now here it is, 9 years later, Jason, and I get to ask you my question.
Yeah, sounds good.
Since discovering Jason 15 years ago, I have been talking about him in my lectures, in my workshops, and in my videos, and I've been sharing his extraordinary drawings of how he sees the world. I think Jason has 2 lives, the life before the incident and the life after. In 2002, while coming out of a karaoke bar, he was badly beaten, and all of a sudden his vision changed. He could see the energy of everything. He can see the energy of your hand, of numbers, of water, of cars whizzing by. And he creates drawings, and they're stunning, they're by hand, to show us that we do indeed live in a world of a geometric marvel of beauty and perfection. And through his remarkable drawings, we get an insight into what our world really looks like. And we learn that there are no real circles.
Mm-hmm. Exactly.
Jason has become a mathematical theorist and has developed the quantum information holography, QIH theory, that our universe is a 3D projection. Jason's book, Struck by Genius, How a Brain Injury Made Me a Mathematical Marvel, is going to be a movie. Welcome, Jason Padgett.
Thanks for having me.
Yeah, hi.
Good to be here.
I'm so delighted that you're here. I really enjoyed your book. I actually listened to it. I do prefer the book, though, because in the book you have a lot of pictures and your drawings, which are a big plus.
Yes.
You have a really good voice. Well, I'm assuming that you narrated your book?
No, actually, we had somebody else do the narrating.
Oh, okay.
Yeah, of the
All
book.
right. It's okay. Yeah. Well, whoever narrated it did a really, really good job, because I felt like I was really hearing it from you.
Yeah. I remember when they got that guy, and he just came across like he understood it a little bit better, and he's kind of sounded similar. So.
Yes, very much so. Another thing that struck me about your book, Jason, is how vulnerable you are. You really shared with us some very private thoughts and events, and that really put into perspective the ups and downs of what you've been through.
Right.
So let's begin with where you grew up and what were you interested in as a young man?
So basically, I was like a typical boy. I was born in Alaska, in Anchorage, Alaska, and life really did revolve around like just chasing girls, especially when I got older. Chasing girls, we'd go out to bars. I did dancing for a while. I actually did stripping in Alaska. We just found an old video of it. It's really funny. But literally, we would go out to
Here's the
bars.
picture.
Yeah,
This
that was
is
me. I'm the guy in the far second to the right with
right,
the spiked
the
hair.
blonde.
I think I
Yeah,
was like 8. I just turned 18 or 17. I was in high school at the time when I did
you
that.
were a bodybuilder. And
Yeah,
here's another picture. I love this picture. Is this you going out on the night
yeah,
on the town? Yeah,
yeah.
with your muscles. Mhm.
Back when I had a mullet. Mullets were in back then, although I hear they're coming back.
They are. Oh my gosh. This is cute with your friend.
Yeah, that was like senior prom night. We were at this little place called the
Um,
Spinard Motel that my friend Kurt there had gotten for me and our 2 dates, these 2 girls.
and there you are. Yeah, you were cute. I can see why you were popular with the girls. Okay. And so you were basically just growing up with like a normal kid into girls and bodybuilding and not really interested in school?
Not at all. I actually remember saying things like, "Oh, math is stupid," or one thing that I remember thinking was witty at the time. I was like, "How does that apply to anything in the real world?" And now I'm like, "It is the real world. It's the same thing." But I just didn't see it, and even most scientists don't see it nowadays. They the equations that they develop are reality. They're one and the same thing. Whereas typically a lot of them think about as this equation describing this, but they're literally the same thing. So
So can you please tell us what happened in 2002?
in 2002, I was in Tacoma, Washington, and I got a call from a friend. She was on a first date with this guy, and they were at this little karaoke bar that was close to my place, and they had a little bit too much to drink, and they needed a ride home. So I told them I'd give them a ride home, and I drove there, and wound up singing. They were singing karaoke, and I wound up singing a karaoke song. Had a Coke, and then we left. And as we left, these 2 guys came out behind us, and they didn't say anything. They were behind me. I didn't even see them. They didn't say anything, and they just smashed me in the back of the head. I saw this white puff of light, like somebody took a picture with a old-fashioned camera with a flash bulb. Like everything went puff white, and then the next thing I knew, I was on the ground, like getting punched and kicked. I found out later from the neurologist that's your brain bouncing on the inside of your skull when you have a concussion. It creates this white light that boxers call a flash knockdown. And that's literally your brain rebounding off the inside of your skull. But anyway, so I was only unconscious from like standing to hitting the ground, and then I came to, and I was just getting punched and kicked by these guys, and it's really strange coming into consciousness after being out like that, because you don't know where you are, how you got there. And I remember realizing I was being attacked, and then thinking, all right, I'm dead right now. I'm gonna die in seconds, and that fight or flight instinct came on. And for some reason, for me, it's always fight, even though sometimes it should be flee. And I remember thinking, I want to hurt one of these guys before I die. And I grabbed his leg because everything was spinning. And I tried to bite him on his leg, but he had on these big baggy pants, and all I got was fabric. And I cracked my front teeth because I bit down so hard. And then I looked up, and the girl that was on the date with this guy, she had just met him. And I looked up and I said, help. And I ducked a punch and I said, God damn it, help. And he put his hands up in the air like this to let everybody know he wasn't involved, turned around and walked away. And I was like, oh man, I'm definitely on my own. And then finally one of the attackers said, give me your goddamn jacket. And I had this little cheap $99 Wilson's leather suede jacket on. And I threw it off. They grabbed it and they ran away. And then it was over. And then I went up going to the hospital. They diagnosed me with a concussion and like a bleeding kidney, gave me a super powerful pain medicine shot, and then sent me home. And I remember noticing how weird everything looked on the way home, but thinking it was I'm still not sure if it was the pain medicine or what. But then the next day, everything was different. When things moved, it looked like picture frames. Like when you're watching people dancing under a strobe light, how you see them here and then here and then here and then here, instead of this smooth flow. And that was the big thing that changed. Everything now is little tiny snapshots that aren't moving, just like you're watching the film of a movie frame by frame by frame. It's called motion blindness or a kinetopsia.
How long did you have that?
I still have it. It's permanent. So when things move, it always looks like it's going tunk, 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 like a strobe light, but really fast. But that's what math and physics is. Like they're saying, here's this particle, and then one moment the particle's here. One moment later, the particle's here. What is the difference between these two picture frames? And if something is accelerating, the picture frames get further apart. If it's slowing down, accelerating where it's slowing down, the picture frames get closer together. So once you see how the images coming into your brain from your eyes visually, once you see them and how your brain is interpreting them, it literally is the same thing as physics. When you go into physics, they teach you these motion diagrams. Like imagine a car is moving like this, and it's moving at 60 miles an hour, and it's moving the same speed constantly. And your brain's taking pictures, just say every 1 second. Really, it's about 25 pictures a second. Then if your car is moving at the same speed, then it takes one picture here, then another picture here, and another picture here. The picture frames are the same distance apart because the car is going the same speed and they're taking the pictures at the same time. But if the car speeds up like this, then the first picture frame is like right here, but the second picture frame is here. Now the third picture frame is here. They're getting further apart as the pictures are taken, and that's what acceleration is. And they actually teach you this in physics, and that's what our brains are doing. When you see a car speed up, you know it's speeding up because your brain is telling you it's going farther in the same amount of time. And when it's slowing down, your brain is saying that object has moved less in the same amount of time. And it literally is how they teach it in physics. It's just they teach it with equations, and we see those equations are describing geometry. So our brain and animals' brains, when they fly, or even any type of animal, they're all doing calculus level equations in the background. We're just not aware of it. So it's really amazing. It's like software, and our brains are just doing it automatically. And it's an estimation, but it's a very close estimation. But it's actually the same thing as what physics is.
So you're seeing things in frames.
Yes, picture frames.
Just in a frame. And does that affect your response time?
No, it doesn't.
Like that?
It doesn't affect the response time now, but it took me like 3 years to get used to it. I had vertigo where it would look like things were spinning and it felt like they were spinning. It was very disorientating, and it makes all objects, like the boundary of an object, doesn't look smooth anymore. It looks like these little tiny straight lines. And that's what led me to this whole thing about how circles don't exist. And they truly don't. But there are things that are close to circles, but circles aren't real. We can go into that now or later, whenever you want.
Yeah, in a little bit, because I still want to talk about the first time you realized you could see the energy of things. Did you realize you were seeing the energy of things?
I at the time, the very first thing I noticed was the day afterwards when I turned on the faucet and water started going down the drain, and it was like little tangent lines, these straight little lines going around, approximating a circle and getting closer together where the radius got smaller and then went down the drain. And it was it's pretty. And I was just mesmerized by it. And very quickly, I can't remember the exact day, but I eventually understood, that, hey, this is mathematics that I'm seeing, but I didn't have the language to describe it, because at the time, all I had was like pre-algebra. I couldn't even graph an equation like in algebra.
And you hadn't even heard of sacred geometry.
Nothing. Literally, all I'd heard of was girls and booze and hangovers, and that was about it. So. But yeah, so I started drawing it because I was trying to explain to people I knew in my family like what I was seeing, but my way of describing it was totally inadequate. And so I started drawing it, and then I had one of my friends that saw it. She's like, you ought to use a ruler and make that straight. It would look pretty cool. So I used a ruler and a pencil to draw it straight, and then it would make it easier to start showing people what I was describing. And in fact, the big like aha moment was I can tell you about that later, but it was when my older daughter asked me how the television worked. and she was watching TV, and she would have been like 5 or 6 at the time, and she just asked me how the picture on the TV changed. She goes, "How does the TV show us images?" And I said, "Well, this just has little rectangular square pixels, and those change colors, and as they change colors, that changes the image on the screen." And right as I said that, a commercial for Overstock.com came on with a big O. And she goes, "You're wrong, Dad." And I go, "What do you mean I'm wrong?" And she goes, "How do you make a circle with rectangles?" And it was like this window went poof. And I was just like, wow, you can't. And then you look in closely at the television screen, you're like, that's not a circle. It's a zigzag of little rectangles, but the pixels are so tiny that your brain smooths it into a curve, but it's not a curve. It's perfect, like little rectangles summing to form something that looks like a circle. And then I thought, well, what if I cut those pixels in half? And then I cut those pixels in half, and I cut those. You can keep cutting pixels in half to infinity, and you still have a circle made with rectangles. It's just the resolution is getting better. And that turns out to be what pi is describing. Pi's numbers, as they go out farther, is describing the resolution of something that, like, I look like I'm a curve, but I'm made with rectangle cells. But if you magnify my skin on a microscope, you'll see all these mountains and valleys. So I'm pixelated, and so is everything. It's just the pixels are so small that we can't tell.
Yeah, I do like your pie story. I want to get back to your pie story. Or you had a couple of professors, one that said something wonderful and one that did not say something wonderful. And I'd like to talk about that and how you dealt with that. But first, going back to when you first realized that you were seeing things differently. So is this always, you always see, always, you cannot not
yes,
see it?
I can't not see it. It's I love it, but at the same time, it's totally distracting too, because it's everything. It's everything and everywhere. And we are all the sums of these individual, what I call quantum state vectors, just those little lines of light at different angles. And those quantum state vectors describe all objects. They describe quantum mechanics, and they describe relativity and gravity. And I can go into that more later. That's quantum hand. That's how, like, if you look at the boundary of that I've sliced that one into like 2-degree intervals. And so the more I slice it, the more smooth it becomes. But I wanted to show people, like, this is what my hand looks like to me. That where all that light is coming from at the center of my hand, that is what's called the holographic projection. It's how all the objects in our universe can be described as a holographic projection from a singularity or a black hole. And so all that light that is bursting out of the center, that's the singularity, and it's projecting the information that is describing my hand onto the boundary of the hand.
Oh, how interesting. Like a beam from a projector, a movie
Exactly.
projector?
Exactly. Black holes turn out, in my theory, black holes turn out to not just be this point in space that nothing can escape, not even gravity, but it also shows that black holes operate like transformative engines. They are literally projectors. Mass is just tangled up light. And so when mass goes into a black hole, it is forced to the singularity where it squishes together and it starts to fuse, and it fuses back into light. Light transforms into mass, and mass transforms into light. So at the singularity, the mass transforms back into light, where it creates an interference pattern like the bumps and grooves on a vinyl record. The singularity is spinning very fast, and it has the bumps and grooves of light waves like the record player, and it is entangled with what's called the holographic screen, which is basically just like a television screen, only incredibly high resolution. That's called the holographic screen, and it surrounds the singularity, and the singularity projects its information onto the screen. So the screen is a perfect mirror reflection of the information at the singularity. So black holes are like, I always say they're like vinyl records, but you can also think of them as like the ultimate streaming service. Like Netflix has a library of movies, and then it streams those movies to our monitors or our screens. The singularity contains the interference patterns of all possible versions of our universe. Hawking radiation is what it connects the singularity and the holographic screen, and it reads that information of the singularity and projects it onto the boundary. So think of the singularity as like the library of Netflix, but instead of having a million movies, it has all possible histories of our universe, which is called Richard Feynman's sum over histories, how all histories potentially actually happen. It is projected via Hawking radiation and entanglement onto the screen. So think the singularity is Netflix. The Hawking radiation is like the streaming through the internet, and the holographic screen is just like our computer monitors or a much higher resolution.
Okay. So,
Sorry.
all right. A couple questions. First, where is that singular beam coming from? What is that coming from? A consciousness? Where is that coming from? And also, can we interpret our own brains to work like that?
Yeah, they are. Our brains are, because our brains are also everything in the universe, which is our universe is the holographic screen. Okay. Everything in the universe, and that means everything, every bit of light, because that composes us, our brain, our consciousness, everything has an exact mirror reflection in the singularity. So it's literally like looking at a mirror. If I look at a little bit of space-time, and we're describing it as zeros and ones in terms of information. If I look at a little unit of our space-time and it's a one, it's a zero at the singularity. It's a zero here, it's a one in the singularity. They're perfect mirror reflections of each other. Just like when you're looking in a mirror and you wave and you see your image waving back at you, but it's reversed. That's what quantum entanglement is. Quantum entanglement, the singularity is entangled with the screen, and quantum entanglement shows that whenever one thing is found, when two entangled particles, or when two particles are entangled, when one is spin up or a zero, the other one is spin down or a one, always. And so it's showing that the singularity is literally what's called our anti-universe, a perfect mirror reflection of our universe. But according to this theory, all possibilities actually, all histories actually happen, but we experience the one that is dependent on our relativistic point of view. So, but according to this, they all happen. Yes.
So we're focused on this particular reality. Are you saying at the same time there's an unlimited amount of slightly different versions of this reality?
Yes, there's a reality where you're interviewing me and where I'm you and you're me. There's a reality, every possible configuration, but it's not infinity, and that's actually really important and really cool. It's called the Bekenstein bound. So Stephen Hawking and this guy named Bekenstein, they won the Nobel Prize, or Bekenstein did, for this. They asked, so if we look at, I show how space-time is composed of these little qubits, which is just these minimal bits of geometry that you can't measure anything smaller than. They're called Planck qubits. And they asked how many ways, so imagine the universe as being covered in little pixels like on your monitors. They asked how many ways can we rearrange the pixels of our universe to create a new and unique history or a new and unique film. And it's not infinity, it's what's called the Bekenstein bound. It's 2 to the 10th to the 123rd power. That's the maximum ways that the pixels of our universe can be reconfigured to create a new and unique history. And what that means is if the universe has an infinite number of big bangs or Big Bang and a big crunch, all that matters is the Big Bang happens over and over again, which is what this is showing does happen. Then after 2 to the 10th to the 123rd power Big Bangs, the histories have to repeat. So what this shows is that all possible histories of our universe happen over and over and over again, and have over and over again in the past and will again in the future. But there's not an infinite number of ways it can be reconfigured. It's 2 to the 10th to the 123rd power. It's a huge number, but it's not infinity, which means that you get to live your life and every version of your life over and over again. Because mass is never destroyed. It just changes from light to mass, mass back to light.
Okay. The fact that you're saying there's no infinity kind of makes me go, what? Because I think we're fractals, correct? And don't fractals just go on into eternity?
Yeah. So this is the weird thing about it. So mathematically, fractals will go forever. So you can make the edge of something a fractal boundary. So yeah, and so mathematically we can do that. So infinity does exist, and I'll go into like velocities of infinity. But the universe has a way of having a minimum resolution that you can't go past. And it comes, just like everything in my theory, it comes from black holes. So if I wanted to measure something that's, say, an inch long, and so I hit whatever that object is with light, it emits photons or light back, and I see the thing that I'm looking at. If I want to look at something smaller, like the skin cells, like on my arm, I got to focus more light onto that little spot to get into all those little nooks and crannies, and then I can see my skin cells. So in order to observe something that's smaller, you have to hit it with more light to be able to observe it. So as you try to observe things in the universe, smaller and smaller and smaller, you reach this point called the Planck length, which is also a Nobel Prize winning equation, where when you try to see or observe something smaller than the Planck length, this incredibly tiny distance, you have to hit it with such high energy photons that it collapses into a black hole and then absorbs the photons, and there's nothing left to observe. So what it means is that you can't see and you can't interact with in any way anything smaller than the Planck length. So everything that exists is made of whole multiples of the Planck length, because something that's 1.5 Planck lengths, the half is smaller than the 1 Planck length, so it can't be observed. So everything in the universe is made of 1, 2, 3 whole multiples of Planck lengths. And so that's how the universe, through black holes, gets rid of infinity for us, because infinity causes all sorts of problems in physics, but the universe gets rid of it naturally for us, because you can only take in a certain amount of data or a certain amount of information because to a certain resolution, because to try to retrieve information from points smaller than that creates a black hole, which absorbs the light that you're trying to see it with. So it's like the universe is pixelated just like a television screen, but the pixels are the Planck length. They make atoms look like the size of galaxies. They're so small, but they're still pixels. So.
Oh, okay. All right. How many black holes are there?
So this shows that if you cover the universe in Planck length or Planck mass black holes, it's the Bekenstein bound. It's literally like covering all of our universe in these little tiny Planck pixels. It is a massive, massive number, but it's not infinity. But infinity is important because so everything in the universe is moving towards or away from infinity. Like imagine, I have an equation that says f of x equals x. So when x is 1, but y is 1. When x is 2, y is 2. So as x gets larger, if x is 1 billion, then y is 1 billion. So as x gets larger, y gets larger, and it goes towards infinity, right? Forever. As x gets larger, the answer goes towards infinity. Now imagine I have the equation x squared. Well, when x is 1, x squared, 1 times 1 is 1. But when x is 2, 2 times 2 is 4. When x is 3, it's 9. It's also going to infinity, but it's going to infinity faster than the other equation. So something moving away from you is going towards infinity faster than something moving away from you slower. So, and it's called the velocities of infinity. It's how you approach and move away from infinity at different velocities. It's weird stuff, but
you went back to school to study math.
Yes.
Okay.
So,
all right. So I asked this question earlier, and if you answered it and I didn't understand it, I'm sorry. But I wanted to know where that original beam came through the black hole to project. Where does that come from?
The black holes come from something called superposition. When you're not, the universe is like a movie. It's going picture frame to picture frame to picture frame. And the frame rate of the universe is something called Planck time, which is how long it takes light to travel 1 Planck length. And there's like 100 billion, trillion picture frames per second. So it's like massive amount of picture frames. But in between the picture frames, just like when you're watching a movie and you see in your movie, when you would see a movie, it's just one still picture and another still picture, like a flip book. When you flip it, it looks like it's motion, but nothing's actually moving on the screen. It's still pictures and just their rate that those pictures change. So this is showing this. So when you're watching a movie, there's a moment in between picture frames when there's no picture on the screen, but you don't see it because it happens so fast. The same thing occurs with the universe. Planck time is the frame rate of the universe, and there we can't see anything smaller than Planck time. It's just like the Planck length. So in between the picture frames, there's a moment when there's nothing on the universe, like but it's incredibly short interval of time where there's no information from that we can observe. Or when I say no information, I mean no information that we can observe. When you're not looking at something, it exists in superposition, where it exists in all possible states. And that has to do with this. Remember, have you heard of Schrodinger's cat, where they put the cat in a, okay, and the cat's in the box, and there's a 50-50 chance that the cat's dead or alive, but you don't know it's dead or alive until you look at it. And when you're not looking at it, the cat is both dead and it's alive. So this is just like that. In between the picture frames, when you can't see or retrieve information from the universe, everything is in superposition. And wherever you have two photons, 2 bits of light on one Planck area, that by definition collapses into two entangled black holes connected by a wormhole. And so that is where these black holes come from, as they form from the superposition of photons in between Planck time. Another good way to visualize it, though, is the Big Bang. The Big Bang, think of it as the source of the projection of our universe. It's the singularity where that information is projected large onto our space-time. So the singularity, or the Big Bang, is the source of the projection.
The Big Bang is the source of the projection.
Yes.
Okay, so in that Big Bang held all the potentials.
Yes,
or
all
eternity.
possible versions of our reality. Yes.
And it's our focus that then creates our reality.
Yeah, it's your position. It's your relative position, depending on what you're looking at, that defines your reality. So, like, even though we all think that we live in the same reality, technically we don't. We are all in this universe. We're all seeing the information, but we're seeing it from different relative perspectives, which actually makes it different. A good way to think about this is like, you hear a car drive by you and it goes, and it changes pitch. That's because short wavelengths of sound make a high pitch and long wavelengths of sound make a low pitch. And so as the car's approaching you, the waves squish together and it gets higher, and then the car goes by you and now the waves stretch out and get longer, and so the car goes, and the pitch gets lower because long wavelengths make a low pitch and short wavelengths make a high pitch. Mm-hmm. But now imagine the car's coming from me towards you. Relative to me, it's moving away from me. So the waves are stretching out and getting longer. So I hear the pitch getting lower. But relative to you, it's approaching you. The waves are getting closer together. You hear the pitch getting higher. And you stop right there and say, what sound is the car making? A low pitch to me or a high pitch to you? And it's making both relative to who's looking at it. Then you imagine we have an infinite number of people all looking at that same car, and they're all moving at different velocities. Everybody hears a different pitch. Everybody's reality is different, but it's just they're relative. So information can be interpreted as any sound, any taste, any sense that exists, and it's relative to who's looking at it. And to that person, that's what it actually is.
Yeah.
So it's really interesting how and color does the same thing. Short wavelengths are blue, long wavelengths are red. So if you had a twin and your twin was standing next to me right now and we shot away from you close to the speed of light, you would see the wavelengths of light of my shirt, which are blue, stretch out and become longer. And my shirt, I'm sorry, imagine it's this red cup, sorry. So red is a longer, I'm sorry, never mind. Let me go back to that. My blue shirt. So blue is a short wavelength. You have a twin and your twin's with me and we shoot away from you at close to the speed of light. Your twin traveling with me will still see my shirt as blue because it's just like she's standing next to me. There's no change. But you would see the wavelength stretch out and get longer and my shirt would turn red. And then you ask, well, which color is my shirt? Red to you or blue to your twin? And it's both depending on who's looking at it.
Yes, and the perspective. And then here we are, we have all these different perspectives trying to get along.
Yes, and our reality is close enough that we can all say, yeah, I agree. This car is generally going this fast.
Kind of,
you don't notice these effects until you get close to the speed of light, and that's what Einstein proved, is how these effects become huge.
Yeah, I love it. All right, I'd like to put on the screen now your drawing of the number pi. The fact that you can see a number. Here is the picture. For those of you who are just listening to the show, I really suggest that you watch the show because my show is very visual. I put up a lot of drawings, and I'm putting up a lot of drawings of Jason. So here is his magnificent drawing of the number pi. And if I remember correctly, Jason, weren't you on campus and you saw a puddle? And
Yes.
isn't that how your love of pi started?
Yeah, it was when I remember it was raining and there was a puddle and I could see like the waves overlapping and creating this beautiful interference pattern. And when I saw the interference pattern, I realized that it's the same interference pattern that I'm drawing when I draw pi and other fractals. And in fact, it was pouring rain, and I was sitting there with this old-fashioned camera covering it up with my body so that it wouldn't get wet. And I was taking pictures of the puddle. And then I looked up and there was a classroom, this one classroom, the entire wall was made out of glass. And all the students were up against the glass watching me take a picture of this puddle, trying to figure like, what the heck is this guy so interested in? No.
Yes. And in your book, you talk about two professors. One professor that you showed your drawing of pi to, and he said, and I quote, this is correct, but only someone who hasn't been taught how to think would calculate pi this way. Who's the student? I have to meet him. This is genius.
Yeah.
I love how he says someone who hasn't been taught how to think. Because
Yes.
that seems to be the problem with our scientists.
It is. They're taught to think a certain way and to do things step by step by step. I call, and I don't mean this in like in a disparaging way, but a lot of scientists are what I call information parrots. They memorize something in a book, they can get the answer, but they don't know what it means. And for me, what I always want to know is why and where does that equation come from on its most basic level, fundamentally. And that's what a lot of them, they don't see and they don't understand. They can only think with what they've been taught. And like when I came in with my drawing of pi, like that you just showed, I thought I was going to walk into class and my professors would go, this is the number pi, and let me explain to you the equations that describe that. And when I showed it to them, I was like, this is pi and circles don't exist. They literally were like, I have no idea what you're talking about. I mean, I could see in their mind that they were like thinking I was nuts, and I was embarrassed. But once I hit calculus, I was able to write the equation to prove it, that what I'm doing is something called integrals with triangles. But calculus does integrals with rectangles. But it's literally the same thing. But I didn't have the language to describe it until I hit calculus. Once I hit calculus and I wrote it in equations that they're familiar with, every one of them has to agree, and they do. They're like, oh, now I see what you're doing. You're drawing it with, but I didn't understand at the time that they saw equations as numbers, not as shapes. Like when I went, what got me to go back to school is I was drawing in the mall, and this guy saw me that was a physicist, and he after seeing my drawings, he suggested that I enroll in math classes, and so I did. And my very first math class, it was just algebra 1. My teacher graphed an equation on a piece of graph paper, and it was just a parabola. And I was like, wait a second, you're telling me that you can graph every equation into a shape? And she's like, yeah. And I'm like, well, I'm just drawing the shape and saying that this shape is on this grid structure of space-time. And you're saying I've got a piece of graph paper, which is identical to space-time, and you're graphing the equation. It's the same thing. It's equations and shapes are identical. They're just two different ways of looking at the same thing. And but I didn't understand that most scientists, almost all of them, don't see it that way. They look at numbers as these magical things that aren't geometry, yet they literally are geometry.
Everything's geometry,
Yes.
Which leads into that one professor. When you explained to him that you see numbers in geometric patterns, and he said to you, quote, there's something wrong with your brain.
Yeah.
You need a new brain. Numbers are not shapes.
Yes. Yeah.
How did you deal with that?
I was actually mad. That's the first time I actually got mad, because it's just the way that he said it was so judgmental, and he was so sure that he was right when he is wrong. But he's looking at it as though, well, I've got a PhD and you're just a student. But that's because he's parroting what he's learned and he's not thinking for himself. But again, at the time, I had no way to prove it. Now I can prove everything that I said to him. But at the time, all I could do was show them these drawings, which was a slow progression of me understanding that, wow, I really do have to write these as equations for the professors because they can't see the end result. And I need to show them step by step by step how their equations are describing this and how they're the same thing, because it's very foreign for them also. So,
weren't you asked to teach some kids in New York fractal geometry?
yeah, I've done a lot of different classes on just fractal geometry, on all sorts of different aspects. The main thing that I always go back to though is pi, because pi is describing arc length, the texture of reality. That's kind of like what fractals are describing, is like the texture of reality and how it changes and how that changes everything about the reality that you're looking at. Like for instance, like distance. Like imagine if you're walking across your lawn and your lawn is like 20 feet across. And so you walk 20 feet. But now imagine you're an ant walking across that lawn. It's going up and down all the blades of grass. And so its size relative to the texture of reality, that's no longer 20 feet. It's a much further distance. Fractals and the way that space-time is composed of these little cubes has to do with the texture or the curvature of reality. Yes, like that.
Here's a beautiful drawing of the wave-particle duality.
And that is like 1, 2,
That's
3,
so
4.
beautiful.
So that is 41 picture or 41 drawings of the exact same shape. So I the very center circle is one shape that I sliced into a bunch of triangles, and then that exact same shape is in 40 different spots. So even though it doesn't look like it's the same shape, that is one shape drawn in different places to make the same shape only larger, which is the definition of a fractal. A fractal is a shape that when you take it apart into pieces, the pieces are the same as the whole.
Mm-hmm. Have you seen the Flower of Life?
Yes. And so have you seen it's space time. Have you seen my E equals MC squared drawing? Oh, if you get a chance, yeah, it's on fine. I wish I knew how to share.
What does it look like? Is it in your book?
It is the Flower of Life. It's the exact same.
E equals MC squared is the Flower of Life?
Yes, it's the 100% identical. So I drew what space-time looks like at the Planck length. And when I got done with the drawing, I'm like, this looks familiar. And like 3 years later, somebody who does sacred geometry was like, oh, you drew the Flower of Life. And I'm like, no, that's the grid structure of space-time. And then they showed me the Flower of Life, and they are dot for dot 100% identical. And I just posted it on a sacred geometry website on Facebook. I'm like, literally, you guys, people who are doing sacred geometry, they're seeing the shapes, but that shape I can describe with an equation, and they're the same thing. Yeah. Mathematicians, they see things as numbers, and most of us see things as shapes, but it's literally two different ways of looking at the same thing.
All right. Okay. So this Flower of Life, and are you seeing God?
This shows, as weird as it is, this shows, so it depends on what people define as God. When I ask people, that's one of the things I like about it, is like the philosophy behind these things. So I ask people like, what do you define as God? And most people say God is like the sum total of everything. And I'm like, well, if that's what you consider God, and that's what I would consider it, the singularity is the sum total of all information, but it's on top of itself. It's all in one tiny little location. So you can't say Seb is here and Jason is there, because everything's right on top of each other as an interference pattern. But when you project it out onto this vast surface area of the holographic screen, it spreads it all out like the bumps and grooves on a vinyl record. And so the singularity is like the record. Quantum Hawking radiation is a type of light that touches the singularity, or it's entangled with the singularity and the holographic screen, and it reads the interference patterns of the singularity and projects it onto the holographic screen. So the singularity is the record, Hawking radiation is the needle or the stylus, and we are the music or the movie playing that is projected from the black holes, from the singularity. It's the same thing. And it's the angular frequency of this radiation that is emitted that describes us. So it's all the same thing. The universe is black holes playing music, every possible composition of music for infinity. and we are the music.
Ah, wow. For those of us who are visual, like my mind, I can just see it and it's so beautiful. So can you say that God is a mathematical formula?
Yeah, this would show that. I mean, I can show that this is the sum over history, like Richard Feynman's sum over histories. We can show that this is gravity, and very specifically, we can show this is gravity, and that it describes, or the rate of change of these quantum state vectors that are. So the flower of life is basically space-time, and on each little hexagon that you see, those little hexagons that compose the flower of life, like hexagons making bigger hexagons, making bigger hexagons. The tiny little hexagon, those are the qubits that you see on the flower of life. And on those qubits, there's just a little line of light. And the angle of that light describes encodes in terms of information, the velocity that's on that pixel, and the probability that pixel will be a 0 and a 1. The rate that little vector of light changes is the rate of change of velocity. And the rate of change of velocity is defined as acceleration, and Einstein proved acceleration is equivalent to gravity. So by having these little bits of light that are projected from the black hole onto the qubits, it describes velocity and it describes probability. Probability is quantum mechanics, and the rate that it changes is describing curvature or acceleration, and Einstein proved that acceleration is indistinguishable from gravity. So this shows that with the geometrical structure of space-time, is velocity encoding, the encoding of gravity, and the encoding of probability. So all quantum mechanics and general relativity are encoded directly into the structure of space-time. It's an information. It's just like a quantum computer. The universe is like crunching numbers through geometry, but that is equivalent to the equations, and we are those numbers or shapes.
Jason, here is the moment that I've been waiting for 9 years. I'm going to ask you my question.
Okay.
Can you see the energy of love?
So amazingly, there is a way to encode this. So this is showing that we are informational constructs. Everything in the universe is information, and information is actually what's fundamental. When you look at this information field, these little vectors tell you velocity. One moment, one little snapshot of the universe, the only information you have is velocity and probability. But one moment later, you get a change of velocity, which describes gravity. So that means gravity arises from the rate of change of the information. So gravity is not fundamental. It comes from the rate that information changes. And so this is showing that basically the universe works like a computer program, like a very sophisticated quantum computer program. So our senses, love, hate, sadness, fear, these are all ways of encoding what we experience and giving sensations to it. Like the sensation of sight is just our brain, or the cones in our eyes, determining the wavelength of light, which is just a distance. Blue is a certain how many nanometers, from peak to peak. Red is longer from peak to peak, but it's all just information. That those wavelengths are read by the cones in your eyes. Your brain interprets those wavelengths and assigns color. Your brain interprets your smell and your taste of, or your sense of hearing, your sense of taste, your sense of touch are all just ways of decoding this information. So all of our emotions are the same thing. Like fear, even though we don't like fear, fear is something that is necessary for us to exist. If you don't fear anything, you see a lion, you walk up, it eats you, and you don't pass on your DNA. But those who have that fear that is encoded into them will be more cautious. And nature finds this balance between the two. So love is something that is good for us, and it helps us to survive, be happier, have kids, et cetera, et cetera. All these different emotions and these different sensations are encoded also, and they all serve a purpose.
And they're a mathematical formula in
Yes.
and of itself. Love is. And can you see auras?
I don't see auras, but I can visualize it. But I don't see it. No, I just see everything as a individual picture frames. I'll have to send you the picture of it, but that drawing of pi, it is the double rainbow. When you see the double rainbow, that is exactly that picture of pi. I'll show you an image. That band, that ring that you see in my drawing of pi, that is Yeah, if you look at a double rainbow that's head on, that ring is called Alexander's band. It's where, like, imagine the center of this drawing. That's light going into a water droplet, and then it splits and refracts all these different directions and interferes with itself at that ring. And that ring is the red, orange, yellow, green, blue, indigo, violet, and the reverse of that for the inner rainbow that you see in the double rainbow. So this is the double rainbow.
Pi, a double rainbow. Okay. And pi is then just made up of a bunch of triangles?
Yes. There's nothing but straight lines in that drawing.
Meaning to a slice of pie.
Literally, yes. It's like cutting the pizza in half, then, or, you know, half and then in half, then in fourths and in eighths and then 16ths, smaller and smaller and smaller until you get to the Planck length, and then you can't slice it any smaller because you create a black hole.
I can't believe how fast time has flown. We only have a couple minutes here, and we haven't even gotten to a lot of your QIH. We talked a little bit about it, but can you please tell everybody how they can find you? Also, your Facebook on your quantum information holography, which I joined, and I love the information. So just tell everybody how they can find you.
Yeah, so I'm on Facebook. I post everything in terms of equations, but then I also write it in normal terms, so it's easy to understand with drawings.
I love it.
So they're on my public profile page and my regular Facebook page. I just started a TikTok, and then also on a site called Zenodo, Zenodo. It's run by CERN. I've published a lot of the equations, and I'm publishing more. So that it's nice because they you can publish there and they timestamp it so it can show when you came up with it, because there's a lot of scientists that are all converging on this, and I had to make sure I published it so that I get credit for it.
Yes, that's good. And do you know when the movie's coming out?
So we're hoping in 24 to 36 months. They just are now doing the screenplay. So they just actually texted me a little while ago saying that they've got this I can't remember what they called it, where they've got the whole basic thing done. Like it's not the whole movie, but like a basic synopsis of it. They have the screenwriter, and they're sending it out to different studios to see which.
Do you get any say? Do you have any say in how it's going to come out?
Yeah, these guys are. They did the movie called A Million Miles Away. It's about an astronaut on Prime Video, and they did a fantastic job. And they're really good. They're checking with everything. I'm going to work with the special effects people so that we'll be able to just like fly into the black hole and see the interference pattern of the singularity and watch the projection of that information appear on the holographic screen. So we're going to be able to. It's going to be fun because we're going to show it moving. I can draw drawings, but they don't show them moving. And I want people to see it moving.
That's going to be good. And who is going to play you?
We don't know. At first, it was optioned by Channing Tatum, but we don't know if he's going to wind up playing me or not. At this point, it's still up in the air who's going to wind up doing it. So. All
right. Okay. Well, Jason, thank you so much.
Yeah, thank you.
I could talk to you for another several hours. This really didn't feel like it was enough.
Yeah, we can do it again too if you want to, because there's so much to talk about. I can't. I talk so much about it. I'll talk about it any chance I get.
Yeah, I would love to have you back. Thank you. And I'm just so honored you're my first guest. Well, everybody, thank you so much for spending your time with me and Jason. And I look forward to the next time we connect. Everything is triangles.
Absolutely.